multi-body dynamics simulations for SAE SUPRA that you guys are preparing for. Before I start, can you just say yes in the box that you have side in case when you can hear me? Okay, fantastic. So I'm sure most of you are familiar with the webinar. You can you will not be able to speak directly. If you have a question, please put it in the question box, or I will try and answer most of the questions that you come up with. Today I'm mainly going to cover multi-body dynamic simulation, and that basically talks mostly about suspension and steering design. Okay, so before we go ahead, let me give a brief introduction about myself. I'm Mahek. I've been working with, I've been doing Formula student and Baha for during my college days in 2008, 9 and 10. I was a scrutineer at Formula Student UK in 2010, and since July 2011, I have been working at Altair as a vehicle dynamics engineer. I've been conducting training for Baha as well as Formula Supra. This is a brief summary of what we are going to cover today. We're going to start by talking about vehicle dynamics, and then multi-body dynamics in general. Give you an introduction to suspension design. Then I will demo the tools that we have that will help you to do better suspension, steering, and brake design. Finally, I will talk briefly about design decisions that you face during suspension design and how you can use HyperWorks to make informed decisions about these things. So I would like to start with this slide, and most of you will be able to guess what I'm showing here. It is the Formula 1 qualifying table from the previous Grand Prix, that is the Belgian Grand Prix. And what I want to highlight here is the difference in between the guy who came first, the guy who came second, guy who came third, and guy who came fourth. And you will see that Lewis Hamilton here was ahead of Sebastian Vettel by 0.02% actually, so even smaller than 0.1%. And the message here is that when it comes to motorsport or performance racing, everything is dependent on the final 0.1%. So the difference between coming first and coming second can be 0.1%. So every little design detail counts, and hopefully you'll be in a position after the seminar to use the tools that we provide you to get that 0.1% advantage to be first. Let me start by talking about vehicle dynamics. What vehicle dynamics is. Dynamics is a branch of physics that is concerned with study of forces, torques, and motion and their effect on motion. What this means is essentially dynamics is implementation of Newton's three laws. Whenever we have any kind of a system of bodies and we know how they are connected, we can apply Newton's laws to determine how they will behave. At the same time, we can also determine what forces and torque each of the body will see. So it's about drawing the free body diagrams and applying appropriate forces and calculating forces at different joints and constraints. We'll see this in more detail later. Vehicle dynamics obviously is is a subdivision of dynamics, where we are concerned with forces and forces and other things that cause the vehicle to move. You can see in the animation on the left that has been created using Altair HyperWorks. What we are seeing here are the different forces that the upper and lower A-arms sees while the car is doing a certain maneuver. And this kind of information can easily be derived by doing multibody dynamic simulation for vehicles. What is multibody dynamic simulation? Multibody dynamics essentially deals with large displacements. There is a very crude way to put it, but it's the key differentiator between multibody dynamics and finite element analysis. When we're doing finite element analysis, the basis of our simulation is material properties, stress, strain, things like the Hooke's law. While the basis of multibody dynamics are essentially Newton's laws. There are cases where people combine the two, but the major differentiator is that in multibody dynamic simulation, the displacements are of the order of the dimensions of the model body. So during FE, the deflections are usually about 0.1% of the dimensions of the body, but in this case, they're much larger. There are two bits when it comes to dynamics. One is kinematic design, and the second is dynamic design. Kinematics essentially talks about how things move with respect to one another, velocities and accelerations, but does not talk about the forces involved. Multibody dynamic software can do kinematic analysis along with force information. So it does a little bit extra than what kinematic design do. So we can do kinematic design with this additional information provided. This slide talks about how different Altair HyperWorks products can be used to do multibody dynamic simulation. Usually simulations are divided into three parts. One is pre-processing, the solver, and the post-processing. Here you see 4 parts. I'll come to the fourth later. But over here we are going to use Altair Motion View to as the pre-processor to set up our simulation. We're going to use the solver Motion Solve, which is a multibody dynamic solver, to solve our problem, and then we will use the post-processing tools Hyperview and Hypergraph to review the results. The fourth block here is talking about how to improve the design once you do all these 3 phases. So Altair also has a couple of products that help you improve the design after you post-process, so that you can close the circle and make more sense out of the simulation results that you have. Let's come to the templates that we are providing. So we're going to talk about Supra today, and we are providing suspension system templates for Supra. These also include templates for Baha, but we'll focus on Supra today. And these templates are essentially ready-made models of a Supra car that you can load onto Motion View, and then you can edit changes to it so that you can model your own car based on the templates that we provide. These templates are designed to be used by students, so they are not very complicated. In fact, they are created by Formula student team members, so the student perspective is held. These templates are parameterized and modular. What that means is that we have set up parameters for most of the things that a student while designing Supra would want to change, and we make a list of these things so that you can change your parameters without breaking anything major in the model. Students can use this out of the box and get familiar with multi-body dynamics, and that is the idea of this providing these entire models to you. It is up to you to kind of deep dive into these models and understand how they work to get a better understanding of vehicle dynamics in general and more so about multi-body dynamic simulation. But the starting point is available as these templates. Let me briefly talk about the suspension design process that generally people follow, or let me put it another way, I would follow if I were designing a vehicle. For suspension design, we usually start off with a kinematic analysis, which is we see how the wheel moves with respect to the chassis and determine whether that makes sense or it is advantageous to us. We will talk about this soon. And we can do this well using half-car models. Half-car models are essentially either we model the front half and the rear half separately, and then at a later point we combine these two and see how the front half and the rear half work with each other. Later the process would be to join the two front half and the rear half and make them into full vehicle models. You can have simple full vehicle models, complicated full vehicle models, and this is where tires come in. And Auto Motion View helps you model tires, which will make full vehicle simulations possible. And then of course, as we spoke earlier, you need to iterate. So once you do the simulations, you need to understand the results, whether they make sense or not, and go back to the kinematic design and keep doing this and keep improving. Today we are mainly going to focus on kinematics and half-car models. And I'll give you a brief introduction to the full car stuff. We have separate tutorials for those. So let's start talking about half-car models. What you see on your right here is a half-car model. It is the front half, clearly, because we have a steering there. And they're usually the starting point of suspension design. So we kind of pick up half the car, the front or the rear, isolate it, and start doing analysis on it. The key factor here is that the chassis is fixed to the ground, and we move the tires up and down so that we can see the compliance interference between the different components as they are moved up and down, and also analyze what kind of forces and kinematics are involved. You will see an example soon. Finally, over here, a variety of designs can be evaluated head-to-head. That means that you can try different half-car suspension types and make decisions on which is the best suspension type based on data you can derive from the simulation. So before we start, I just want to give you an introduction to a basic suspension and make sure that we are on the same page in terms of terminology. I'm sure most of you all know that this component here is the tire. What you see as little orange sticks are the upright or the knuckle. We don't really model it as a big component. It's just the 4 points that are important. So it's a stick figure of an upright. Spring is pretty obvious. I will call the lower wishbone or the lower A-arm the lower control arm because it's a more general term for any type of suspension. So whenever I say lower control arm or upper control arm, I'm referring to the wishbones or A-arms or whatever else you might call them. Then the lower control arm is connected to the upright by the lower ball joint, and the upper control arm is connected by the upper ball joint. We also have a tie rod that is hidden towards the back. In the front suspension, the tie rod connects the steering and the knuckle, and in the rear suspension, it usually connects the vehicle chassis to the knuckle. So the two ball joints and the tie rod ball joint hold the knuckle in place and allow the wheel to move only in the rotation direction. And as the suspension moves up and down, you can see on your right, this is how a suspension moves up and down. And we will, and this simulation comes from a very basic simulation in motion view, and we can derive a lot of useful information from a simulation like this. So before I do a demo of the templates in motion view, I'm going to briefly talk about the two most important type of analysis that we kind of do with half cars. The first one is ride analysis. So both the wheels are moved up and both the wheels are moved down at the same time. This is a situation when you are hitting a bump, and we can clearly see this happen imagine this happen in a normal situation. You might design the vehicle for different different wheel travel, so the amount of wheel travel you want to put in the simulation is user defined. The second analysis that is important is called the roll analysis. This is very similar to the ride analysis, but the left and right wheel move out of sync. So when the right wheel moves up, the left wheel moves down, and vice versa. This simulates roll in the chassis. What is roll? When a vehicle is cornering, you will see the vehicle roll about an axis, and this is because during cornering, due to the lateral force, there is weight transfer that happens. The weight transfer causes the one of the springs to expand and the other to contract, thereby causing the car to roll. Again, in roll, the wheel travel can be user defined, so that it's different because it's different for different people. So before I move on with this, I'm going to do a quick demo of the motion view tool. If anyone has questions, they can go ahead and ask. Okay, I assume there was no noise, you couldn't hear me, so I'm going to repeat this really quickly. You can start motion view by going to your start program files, and you will see motion view inside your HyperWorks installation. When you click on that, an interface like this will show up, and this area is called the graphics area. This area is called the browser. This is the panel. All the components you will see in the browser, all the component properties in the panel, and all visualizations in the graphics area. And you start noticing this soon. Okay, so to start off, let's load a model. For that we go to File, Open, Model, and go to the place where you have extracted the library from the website that from the Alter Hyperworks website. And when you extract it, you will see a folder called Student Vehicle Library pop up, and inside that you will have two subfolders, one for Supra, one for Baha. We worried about Supra right now. And you can start off by loading a complete model, either for the front or for the rear. For demonstration, I'm going to use the front, but the rear also is very similar. When you load these templates, it is important to remember that as soon as you load these templates, a message box will pop up with an error. And if the error is of type table data, you can safely ignore it. You can say clear and ignore the error. What you see has been loaded here is a front half of a vehicle. You can use these to move things around. For example, if you want to view this from the top view, side view, front view, and as you can see, this is perhaps more clear. This is a push rod type front suspension. You can also we also have a normal SAE suspension, but I'm going to do the demo using this type of suspension because it's frequently used in Formula Supra events. This is very similar to the SAE suspension, apart from the fact that when the wheel moves up, this rod also moves in this direction. This point is connected to the chassis, and the rocker will move in this direction, compressing the spring. Okay, and what you see here in the browser area now, in this browser area, is the different components. For example, this is the suspension, this is the rack and pinion steering, and these are the analysis. You can a blue folder with a circle inside is a system, is a suspension subsystem, and a blue folder with a triangle inside is an analysis. As you can see from here, at a given time, only one analysis can be switched on. That essentially means that at any given point in time, you can do only one type of analysis on the vehicle, and then you have to choose something else to do a different analysis. For example, if you want to do a ride analysis on this vehicle, you click on the right click on the ride analysis and say activate. What will happen is that the single wheel analysis that is highlighted right now will get deactivated, and you will see a static ride analysis pop up. So now the static ride analysis is selected. So first I will explain how to change points around in your the suspension hard points around in the simulation, so that you can move from this sample car that we have here to your own car. You next to every subsystem you will see a plus sign, and you can next to every system icon you will see a plus sign, and when you expand that you will see a whole bunch of folders that pop up. The important folder for all of you is the dataset. When you expand the dataset, you will see a dataset called vehicle input parameter front, and this is the most important thing that you have. When you click on something on the browser, you will see the appropriate properties will show up in the panel area below. In the panel area now you see a different bunch of inputs. You can click on this button here to pop the panel out, and here you see a list of different parameters that you can change to modify your suspension assembly. For example, this one is the you can use this to change the X coordinate of the upper ball joint. You can use this to change the Z coordinate of the lower ball joint, of the upper ball joint. As you can see, the coordinate system that we use is the X-axis pointing towards the back of the car, the Z-axis pointing vertically up, and the Y-axis pointing to the right of the driver. We would highly recommend that you stick to this coordinate system orientation, although you can move the origin around as long as the XZ plane is the plane of symmetry. So the full vehicle model that we have is a symmetrical model about the XZ plane. So if you change something on the left, a similar thing, the same thing will change on the right as well. So the origin is free choice as long as the X and Z axis is the plane of symmetry. All the coordinates can be moved around by using this data set. Okay, the question I already have is where does the origin lie and can we move it? As I said, by default we have assumed that the origin is somewhere in front of the car. Can you move it? The answer is yes, but please make sure that the XZ plane is the plane of symmetry and X points towards the rear of the car. This model is a template model that has been prepared with this convention in mind. So to change the coordinate system to something else will not be a very easy task. It's a tedious process. I would highly recommend that you keep the XZ plane as the plane of symmetry, but you can have the origin anywhere you choose on the XZ plane. Moving on. So you can. So I just quickly show you in the front view. So this is the front view of the vehicle, and we are going to change the Z coordinate of the upper ball joint from 377 to say 300, and you can see that move in the model itself, right? And similarly, you can move the lower ball joint Z direction to say 200, and now you have the lower. You can see the lower ball joint move up and down. Similarly, you can change the position of the wheel center. You can change the position of the chassis pickup points. That is the point at which the control arms hit the chassis. These are called the LCA front bush. LCA stands for lower control arm. UCA stands for the upper control arm. And what is the front bush and the rear bush? Essentially, if you look at in the side view, the A-arms are connected to the chassis at 2 points. Are connected at 2 points, and this one here is known as the front bush, and this one is here is known as the rear bush. So these are the points where the suspension is connected to the lower control arm. It's okay if you do not have a bush here and you have some other type of joint, but it's important that this point be the center of that joint. And the front and rear is with respect to the driver, or front and rear of the car. So also the points of the different points of the suspension can be moved around. This component here is called the rocker. It's essentially a triangle, and you can change its dimension significantly by moving the coordinates around. So it is highly recommended that while you are working with CAD or directly working with MBD models, these are the parameters that you change one by one to evaluate your suspension design. So once you have set up a model according to your own preferences, I missed one thing. You can also change similar things about the steering through the steering input parameters dataset, and there are different steering parameters that you have that you can change through coordinates, through the coordinates. Remember that the default coordinates for motion view is millimeters for length, and although you can change it by changing the solver units, again it is highly recommended you do not change this around too much, because that upsets the balance of the sample model that we have provided you. For example, if you change from the length units from millimeter to meter, you also have to change your spring stiffnesses to go from Newton per millimeter to Newton per meter. Similarly, when you look at the individual analysis, they also have their own data sets, and you can change different things by modifying different things in these data sets. For example, in this data set, we are adjusting John's travel and rebound travel, which means this is currently this means that each wheel should move 50 centimeters in the upper direction and 50 centimeters in the lower, 50 millimeters in the upper direction, 50 millimeters in the lower direction, and you can change this around by changing these parameters here. Similarly, you can change the other vehicle parameters that you might know, like the tire vertical spring rate and tire static loaded radius, CG height, and things like that from this data set. These things affect the solutions that you get significantly. So make sure that you change all these parameters as per your car. And also, if you do not understand a certain parameter or do not have values, for example, for tire vertical spring stiffness, it's okay to use the values that you see here. They're reasonable. So that is how you change things around in the model. Does anyone have questions about this so far? Okay. Okay. And you can also change the toe and camber from this dialog that you have here. It is static toe and camber. Is there a template without the rocker arm? Yes, there is a direct actuation template. And do we have a monoshock? I think we have received this query from somebody, and we are trying to provide you with a template. But while we do that, we also recommend that you go through the current template in detail, so that it doesn't take too much time for you to understand the monoshock template. It will be slightly more complicated than what you might see here. These templates are provided on the website, and we keep updating the website with better and newer templates. So you should keep visiting often. By the end of today, we should have uploaded the templates for the SAE suspension without the rocker arms, and Hello? Yeah. So there was a disturbance here. So I think that's all the questions that we have so far. So next we will look at how to go about doing an analysis. To do an analysis, let me first load the default model again. So first we select the appropriate analysis. When you select the analysis, you choose the activate button and the appropriate analysis will be chosen. And after that, what you should do is, if you see the on the top of the browser, there'll be a line called model. Right click it and then say apply attachment candidates. This will throw up a pop-up, may or may not throw up a pop-up. If it does, click on auto resolve attachments and close this. What this does is it sets up the template for you. By default things are set up, but when you change things around, you need to, every time you change something, you need to do apply attachment candidates and auto resolve attachments. Once this is done, hit the run button. For everyone's information, whatever I am describing right now, including this exact process to follow, has been documented and uploaded on the website that where you see the videos for the different analysis that you do for Supra, and you can read these documents and follow the tutorial line by line. So you do not really need to write this down somewhere. Anyway, so what you see here is when you hit the run button, you will see the run panel show up. When you see the run panel, first thing you need to do is choose a working directory where you're going to run the simulation, and that you can do by choosing by clicking on this button here. And I'm going to choose my running directory, and I'm going to call it demo. And you need to give a file name. So let's give this file name ride webinar. Save. So here in my case, demo is the working directory, which is fdrive supra demo, and all the simulation related files will be written down into this directory. Now to run the simulation, first thing you need to do is click on this button called check. When you click on this button, a pop-up will show up and it will go ahead and check the model in motion view. If there is an error in modeling, it will show up here, and you will see an error here, and you would need to resolve it first. Usually when you see an error in while clicking on check model, most often you have forgotten to do the apply attachment candidates bit, and you should do it again and go to run and try check model again. Once you have a clean check model with 0 errors like you see here, you can hit the run button to actually do the simulation. When I click the run button, a pop-up will show up again. The pop-up is actually motion solve, trying to solve this model. It will open a white window. It will run through the solver, and in the end it will say job complete after it has done the simulation. There you go, job completed. So once it is done, job completed, that means that your simulation has run through. Once you have run the simulation, you will see 2 extra buttons in the run panel that get activated: the animate button and the plot button. So let's first view the animation. So to see your suspension move about, you can click on the animate button, and what you will see is that your HyperHost window will split into 2, and on the right side it will actually be loading HyperView, which is, if you remember, the post-processing tool for multibody dynamics in HyperWorks, and you will see the toolbar change significantly. Here you can hit this play button here to view the animation. So since we did the ride analysis, what you see here is the animation of the ride analysis. You can see it in different views by using the same toolbar as before, and here it's really clear what the suspension is trying to do. We can see the wheel move about, and I will also show you how to measure different parameters about your suspension. So once you look at the animation, that is essentially visualization of your suspension moving up and down, and secondly also confirmation that your simulation has run correctly. After that, we can click on the left window again and go back to motion view and our run panel. What we're going to do now is try and plot a few results that we might be interested in. When I click on the plot button, the graphics area will split into more windows, and you will see a hypergraph loaded. In the toolbar, you have another button here which you can use to maximize any of these small windows. So we are going to maximize the plot window here. What you will see when you start the plotting tool is a new set of properties in the panel below, and a new set of toolbars. So this is essentially hypergraph. The first thing to remember for the Supra models, the templates that we have created, is that when we run the simulation and click on the plot button, by default you will see a .abf file loaded. If you remember, fdrive Supra and Supra/demo was my working directory, and the results file that is loaded is a .abf. To make more sense out of out of the results for our interest, what I would recommend is remove the ABF extension and replace it by a PLT. This instruction has been documented in the document that is provided, and what this does is it filters only the results that we are interested in and ignores the more general results that we can also plot. So in this panel, what you see here is there are two sections. First is the Y type, and second is the X type. Y type determines what you want to plot on the Y-axis, and X what we want to plot on the X-axis. And you will also see three boxes. So suppose we want to plot a displacement of something. Then you click on displacement. Then it lists the list of things for which you can plot displacement. So let's say we want to plot the displacement of the wheel center of the left wheel. When we click on this, you will see the final component window get activated, and then you can select which component. So do you want to plot the X component, X displacement, Y displacement, Z displacement of the relevant component. You can also choose to plot the magnitude, which I'll choose here. So this is a sample graph that is plotted against time. Let's go to more useful results, or things that you might be interested in. You will find in the user defined section. When you click on user defined, it opens a whole bunch of interesting results for us. For example, the roll angle, the caster, the camber, the kingpin axis inclination, the toe, steer, camber angles of the vehicle, the stiffnesses of the tires, etc. This you can choose whatever you want to plot. If you see something of the type toe, steer, camber angle, that essentially means when I select this, if I plot X, I will plot the toe. If I plot Y, I will plot the steering angle. And if I plot Z, I'll plot the camber angle. So right now let me plot toe. And this is toe with respect to time. This usually does not make sense, and you would want to plot something not with respect to time, but with respect to wheel travel. So to plot the same curve, the toe against wheel travel, what you need to do is now choose the x coordinate. X coordinate, we will not choose time, and we will go to user define and choose wheel vertical displacement. When I choose that and say apply, now we have a curve of the toe angle of the vehicle with the displacement of with the vertical displacement of the left tire. When you this is more useful information, and can be the slope of this graph is essentially the toe gain when the wheel moves up and down. Hypergraph is really a powerful tool, and you can find derivatives and other things by just right-clicking on the curve, and you can find the derivative, integral, double derivative, etc. of any of the curves that you might be interested in. So coming back, so that is a sample model being run for you, and so to revise, what we did was in motion view, first we went to the different subsystems, went to the data set, changed the points to our liking. Once we did that, we chose the analysis that we wanted to do, activated it, did the apply attachment candidates, hit the run button, and simulate the results. You can view the animation, and you can plot whatever results you want. Now let me quickly show you how to switch from one type of simulation to the other. It's really simple. Now suppose you want to do the role analysis, that is the other analysis we spoke about. Right click on it, say activate, and you will see the ride analysis get deactivated, role analysis get activated, and you go to model, right click, apply attachment candidates, auto resolve attachments, and now you're ready to do the role analysis. Click on run, choose a different name so that you don't overwrite your previous results, and as soon as you do that, you will see the animate and plot button disappear because you have not done run. Before run, you should always do a check model. So check model says that everything is okay, hence I can hit the run button, and you will see again motion solve pop up and try and run the simulation. Similarly, you can click on the animate button again and split your screen further and view the animation. So now this you see is the role analysis. You can see that better in the front view. So you can see that the left wheel and the right wheel are moving out of sync, up and down. And you can plot those results at the same time as well using the same method I just described. So that is a brief demo of how to run a simple model, the default model that we have, and you can change things around as per your liking. So I'm going to stop here for about 2 minutes, and you can ask questions if you have some so far. I will cover directly actuated suspensions just in a minute or so. Okay, so we'll continue. So when I was taking you through the templates, I remember I told you that these models are also modular. What that means is that you can remove the, so suppose you want to go ahead and do the, instead of using a push rod type suspension, you want to use a direct actuation suspension. You can remove this type of suspension and add your own one. I'll just show you how to do that. Click on the right click on the suspension that you want to get rid of, that is the front SLA suspension that we have here. Click on delete, and when you confirm the deletion, you will see the suspension disappear. Now you need to add new type of suspension. For that, you click on model and import. You can, in the panel, you can scroll down to the import button, and then go in the library that you have downloaded. There will be a folder called components for customization. In that you will see a suspension folder, and in the suspension folder you will see different types of suspension. So what you had right now was the front push rod suspension. Now we will choose the front direct actuation suspension. Say OK and click on import. This type of pop-up will come up. Say OK again, and you will see this type of suspension loaded. This is the direct actuation type suspension that many of you might be familiar with. To get this working, again you need to right click on models, click on apply attachment candidates, auto resolve attachments, and then say close. Once this is done, you are ready to solve this type of suspension. So then again you can choose the ride or roll analysis as per your liking, or any other analysis. Activate it, apply attachment candidates, auto resolve attachments, and then hit the run button. Choose your working directory. Ride direct. Save. Check model first. The model seems to be okay, and then give it to the solver to run. So this is how you can replace an entire one type of suspension with another type of suspension. You can do similar things with the rear suspension as well. And when I click on animate, the screen will split into two again, and you will see the animation happen. So this is the right analysis of the direct actuated suspension for a Supra model. Coming back to motion view, let me pause the simulation. Coming back to motion view, even this one, you can change parameters around by moving things in the data set, which is similar to the other suspension that I just showed you. So you can change the parameters by changing the things here. Similarly, you can do the roll analysis as well. So does that answer your question about direct actuator suspension, whoever had one? Okay. So this ends the demo of the tool that I was going to cover. There is one more thing that we have that might be useful. That might be useful to know. Sometimes what you want to do is plot a whole bunch of results so that you can see, you can compare different simulations together, and at the same time see as many of the plots to compare as possible at the same time. So for that we have created something called the hypergraph templates, and I'm going to show you quickly how to use them. They're really useful and powerful thing. So let me start by creating a new session, or go to Start, Program Files, go to the HyperWorks folder and select hypergraph. When you select this, hypergraph will be loaded like you see here, and then you can go to File, Open, and click on Report Template. Here you can browse to wherever you have downloaded the vehicle library from our website, and go to Components for Customization for Supra. Here you will see hypergraph, a folder called hypergraph templates. Since we did front half car analysis, we're going to choose the front half template. Open, and you will see a different panel show up again. Over here you need to select the simulation you have done, you want to see the results for. For example, when I did this simulation, you remember I chose the working directory and the simulation name as ride-direct. I can go to hypergraph, browse to that same directory, F-drive, Supra, demo, and let me choose ride webinar PLT. So the important thing is you have to choose the PLT file, that is the plot file, PLT file, and say open. When you say apply, and this is going to take some time, but what it's going to do is it is going to plot all the things that it finds useful. For example, what you see here is the steering angle, and since we didn't give the steering angle of 0, it is 0 for the left wheel displacements. As the left wheel moves up and down, you can see that the steering torque is 0, and at very high angles you see some very little torque. But this is more useful in seeing things like the camber angle. So on the top you see the left camber angle, bottom you see the right camber angle plotted against wheel displacements, and these are very useful plots. So this means that as your wheel is moving up, your camber is actually going down. As your wheel is moving down, your camber is going up.